Hello everyone, this is the class project presentation for Goktug Cinar for EEL 6562 Image Processing and Computer Vision at the University of Florida. The topic of my project is comparing various hidden state estimators for object tracking on foreground objects extracted by Correntropy filter. Here's an overview, an outline of my talk. I will first be talking about the Correntropy, which is a measure of similarity that we are using in our methods. Then I will talk about video background estimation and a method that I have developed a year or two ago to do background estimation in videos. Then I will talk about the blob detection method that I borrowed from a student in the University of Toronto. Then I will talk about different hidden state estimation problems. These filters will include the Kalman filter, Correntropy filter, and variations of the Correntropy filter. Then I will be outlining the results and conclude the talk with some remarks. Consider two scalar random variables x and y in real numbers, and the cross-correntropy is a generalized similarity measure between two arbitrary scalar random variables x and y, and it is defined by the expected value of the kernel whose arguments are x and y, which can be written as this double integral over x and y of the product of the kernel evaluation times the joint probability distribution. The kernel can be any continuous positive definite kernel, but in our project we are choosing to use the Gaussian kernel. There are some nice properties with the Gaussian kernel, and those are the reasons actually we are using the Gaussian kernel. We will use the sample estimator instead of the expectation operator, so instead of the expected value here and the double integral, we will reduce it to this sum, whereas the estimated Correntropy will be the single sum normalized by the samples that we have. When we use the Correntropy, these are the properties that really makes Correntropy a desirable method to use. It is positive and bounded, reaches its maximum if and only if x equals y when we use the Gaussian kernel, so that's a very nice property of using the Gaussian kernel. And also, as we are using the Gaussian kernel, the Correntropy is the weighted sum of all even moments of the random variable x minus y. And this actually comes from the Taylor series expansion of the Gaussian kernel. If we expand the Gaussian using the Taylor series expansion, we see that it is basically the expected value of x minus y to the power of 2n. Therefore, the sigma becomes a weighting factor for the importance of the different moments. So now, as we all know, correlation is a very famous similarity measure, but it only uses the second order information in the signal, where we now have a method that can use all even moments of the signal. So this is a huge advantage. The problem of hidden state estimation is as follows. We assume the system will be described by two equations. These will be the system equation and the measurement equation. The system equation basically tells us how the hidden states of the system evolve in time. We assume a linear model here, so xk at current time is just f times xk minus 1 plus an uncertainty value or a noise value, you may say. And then the measurement equation is the relation of these hidden states to the measured variables that we have access to. And the measurement matrix H is a linear relation between hidden states and the observed variables that we have access to. Vk is the uncertainty in this equation, or the noise, again, that you may say. We assume that the Wk and Vk are independent, zero mean Gaussian noise processes with covariance matrices Qk and Rk respectively. These are the main assumptions, especially when we use the Kalman filter. So, Correntropy filter. Why don't we use Correntropy in a cost function and use the nice properties of Correntropy in the hidden state estimation problem. We actually know that the Kalman filter can be derived by a quadratic cost function, and solving this cost function by equating the partial derivative with respect to the hidden states to 0. So rooting from that, we decided to come up with a new cost function using Correntropy, whereas we will have two terms here, and those two terms basically represent the uncertainties in the equations, such as the first term is yk minus hxk, which is the measurement equation uncertainty, and the second one is xk minus fxk minus 1, which is the state transition system uncertainty. As we have used before, we will use the sample estimator instead of the expectation operator, and we will use one sample estimation to use the instantaneous gradient. Thus, we can find the best estimate for the hidden state by maximizing the cost function with respect to xi. We can separate this cost function into two parts, and the gradient then will be as follows for each part of the equation. We have used gradient ascent in this algorithm, so this introduces a free parameter, which is the step size, which has to be chosen with respect to the application. We use this filter for background estimation, where we will show that the free parameter selection is important but not as crucial. Also, the other free parameter in the system is the kernel size, which is a common problem in information theoretic learning problems, and we will be talking about those in the variations of Correntropy filter. So what is the background estimation problem? We assume that there is a filter for each pixel. Each pixel in the current frame of the video feed is the observation, the RGB values. We assume a three-dimensional hidden state for each pixel, and each dimension will correspond to the RGB values of the background estimation. We will assume that the system transition matrix is identity, and the measurement matrix is also an identity matrix. Why do we make these assumptions? First of all, the system transition matrix defines how the states evolved, as we said before. And in a background, we don't expect the states to evolve in terms of huge changes throughout the time. We want them to be steady. So the identity matrix says that the states do not move, they only can be jittered by the system noise. And we want all the incoming new information to directly reflect to the hidden states of the system. That is why we choose the measurement matrix as identity matrix. I will show you a video of this background estimation. We use the Correntropy filter, as we said. The nice, very intrinsic property of the Correntropy filter is the resistance against outliers in the data. So what we have done, we took a video from the PETS 2001 dataset, the parking lot video, and we added salt and pepper noise to it. The salt and pepper noise will actually be captured by the VK in the measurement model, whereas the moving vehicles or moving people will be captured by the WK. And when we minimize the effects of those two with this cost function, we should be able to remove all these moving objects from the current frame as well as the noise. Why can't we use a Kalman filter for this problem? Because the Kalman filter will move towards these outliers as it has a quadratic cost, whereas the Correntropy filter will just neglect these if they're not happening very frequently. So in the top left corner we have the current feed. On top right we will have the foreground extraction, which is basically subtracting the foreground and background. So subtracting the background estimation from the current frame. We can do, of course, smarter things such as masking, which we do in the project, but this video is actually about showing how the background estimation works. So as I said, the left top corner will be the current feed, and the bottom right corner will be the background estimation. We initialize the system with the first frame. Now we see in about 8 seconds all the noise effect is removed, and even though there is a person moving in the top left, in the bottom right we don't see a person moving. They will get into their car. They will back up the car in a second. And then we will see that this movement will be captured by the filter. There's a new car in the scene, he will be parking, and this car will be leaving. Now we see that the system adapted, and the car that have left the parking lot is no more a part of the background, and the car that parked is now a part of the background, which as it should be. That is the adaptive background property. Actually, in one point in this video, one of the windows starts shining because of the movement of the sun, the illumination change, which is a big problem in background estimation. And the filter will just, in milliseconds, adapt to that, and we won't even notice that difference in the foreground estimation. So once we do the background estimation, we will extract the foreground by simply looking at the difference between the current frame and the background estimation, and we will create a mask for the foreground object. In this paper, we will assume only one single moving object throughout the frame for simplicity, but this model can trivially be generalized to accommodate any number of moving vehicles or moving objects in a frame. Then we will use the blob fitting algorithm that we have referenced to detect the center for a blob of a given radius. The algorithm creates a prototype, which is a filled circle of given radius. Then the algorithm operates by sequentially subtracting prototype functions from the image at the peak cross-correlation locations between the image and the prototype. As we have an adaptive foreground extraction method as the pre-processing step, this simple blob fitting algorithm performs reasonably well because people usually do difference from frame to frame, which will give them the edges of the object, most of the time in one direction, and this will be a much more noisy data. We will have much better and fully connected bodies as we use the background estimation, and even this simple blob detection algorithm, as I said, will perform reasonably well. So why do we want to do hidden state estimation on top of this? It is because the blob detection algorithm, even though it's performing well, it's quite noisy. It will jitter, it will not always converge to the exact center. So we are hoping by using hidden state estimation models on top of the blob detection, we can improve the estimation results. Among many ways that Kalman filter can be formulated, as I said, it can be formulated by this quadratic cost function. And I just here present a review of the Kalman filter. We have an a priori state estimate, which is the naive guess, your previous guess times the state transition matrix. Then we propagate the error covariance matrix with the given rule. Then we find the measurement error for the current measurement. This is how well we can model the current signal. Then the innovation covariance is calculated, which is then used to calculate the Kalman gain. And a posterior state estimate is given by the current estimate plus the plus the measurement error corrected by the Kalman gain. And then the a posteriori error covariance matrix is found. This is the beauty of the Kalman filter. As we propagate the error covariance matrix, all the information about the past is encoded in the error covariance matrix. As I said, we will also be using variations of Correntropy filter in this paper. These are fixed point Correntropy filters with adaptive kernel size and fixed kernel size. So instead of using gradient ascent, now we defined a fixed point update rule by equating this partial derivative to 0, which then gives us the update rule in this line, and we then notice that this term here is the norm of 0, which basically cancels out some of the terms here and then simplifies the update rule to this. We notice that the kernel size effect, which I talk more in deeply in the project report, these are all taken from my previous paper to IJCN International Joint Conference on Neural Network, where we published these filters. So I have used that paper and the explanations in that paper in this project to give the background information. And we come up with a heuristic adaptive kernel size rule by selecting the kernel size, such as for a dynamical model, for object tracking, we will be using Ramachandra's model. This is basically 3 equations that define the relationship between the position, velocity, and acceleration for each axis. T is the sample time, and AI is the noise term that accounts for maneuvers and acts as driving force of the system. In this model, we assume that the measurements are the position, and we have the same equations for both coordinates. Therefore, we use the following F and H matrices in our linear dynamical model. As I said, x is the position, x dot, the first derivative is the velocity, and the second derivative, x dot dot, is acceleration. We use the video from YouTube to perform the tracking operation. This video displays a plane taking off from an aircraft carrier. The plane performs a vertical liftoff till it reaches the edge of the screen, then drops while doing a flip, and then flies away. I hand labeled the data frame by frame for the center. Here I am showing one of the centers, one of the frames during the vertical liftoff. The blue line shows the overall path that the center of the plane body follows through the picture, through the video. We will use these ground truth to compare the performance of the algorithms. We use the blob detection with 4 different radiuses: 10 pixels, 15 pixels, 20 pixels, and 25 pixels. We obtain the best results for 10 pixels. Here on the top left, the figure shows the trajectory of the ground truth and the estimation algorithms for radius of 10 pixels. Also in the right, I will show the state 1, which is the x-axis, and the performance of the original hand labeled truth and the estimations. On the bottom left, I show a zoomed in version. I zoomed in around this area to show the effect of the noisy blob detection and the improvements that are introduced by the hidden state estimators. And bottom right, I show the PDFs of the errors. We see that the blob detection is quite jittery, especially in the area that I've zoomed in. And we see that especially the C filter, the Correntropy filter, the original version, is really neglected with respect to these outliers. Therefore, we expect that when we look at the video, which I will show, that it performs much better. It will be a less noisy tracking. And we look here for the error PDFs. We see that, especially in the Y direction, where the main motion occurs, the PDFs are narrower and peakier for the estimations compared to the blob detection. In the x-axis, the blob detection has a more peaky state estimate, but it also has a heavy tail, which is reduced by the filters. So we actually got rid of the outliers, even though towards the center, the blob detection made a better job. Here are some tables that are showing the MSE for all the methods compared to the ground truth. We see that especially for the 10 pixels. We see big improvements, mostly in the Correntropy filter, but all the filters actually improve the results. In 15 pixel case, still all the filters improve, but not as much, which is also visible in the PDFs. All the PDFs are pretty much the same, except the Kalman filter, which is inferior to rest of the models because it's a linear model and it is very open to noise. But on this bottom left, we see the figure that shows the trajectory for the radius of 20 pixels. And notice that there is a bias, there is a shift that occurs because of the blob detection. So the main bottleneck of this overall model appears to be the blob detection, because the hidden state estimators cannot magically fix this shift here, but will always make the estimation less noisy and less jittery. These are the PDFs for 20 and 25 pixels, where as we grow in pixel size, all the performances stay pretty much similar, and these are also visible through the tables. There's still an improvement, but very minimal when we use the hidden state estimation. So let me show you the video for 10 pixels. So on the left, I show the video with the white circle representing the blob detection algorithm. On the right, I will show the processed video where the white circle will still be there to show the blob detection algorithm's performance, and the black circle shows the Correntropy filter's output for position estimation. We will see that the white circle will be much more jittery, but the black circle will be smoother in motion and will be following the changes more smoothly rather than sudden jumps that the blob detection performs. So here you see that these outlier white circles happen, and when they happen like not prominently, the black circle just doesn't care about them. When they start to be prominent in right now, then the black circle will shift towards it. We see that still the tracking happens here. For an error, it focuses on the tail, on the wings, and then it follows. So especially around these points, you see that the white circle and the black circle are not at the same point, which is because the white circle is performing an outlier, a jittery estimation, whereas the Correntropy filter, the hidden state estimation, improves on that and doesn't care about these sudden changes, which are basically measurement errors. Here are the codes. I will be submitting these codes along the presentation. The background estimation is protected by a patent that we have applied, so the code will not be distributed, cannot be distributed before prior consent. This is the main method where we gather the video frames and use the adaptive background estimation. The blob detection, fit blobs, is the code that we have borrowed from MATLAB Central to do the background estimation. The code is developed by Alexander Forley from University of Toronto. The add circle is another method we have used from the internet. We have referenced it in the paper. I did not use it exactly the same. I have modified it to better serve my purposes. This is the code that creates the detected centers and shows them. The tracking result basically generates the results for each center. For instance, for pixel size of 10, all the filters are applied in order. So as I said, this is the trajectory. You see that the tracking is much more noisy, whereas the cyan line, which is the C filter, doesn't care about these outliers, and even the common filter and the other filters are much less responsive to these noisy measurements. Here is a closer look at the error PDFs. As I said, the tails are lowered when we use the hidden state estimation, and especially in the second axis. The PDFs are peakier and narrower, except for the common filter, which we expected to not perform very well overall. And this is the noisy jittery measurements as I have shown, and you can see that the other filters are less responsive, whereas the common filter really heavily responds to these outlier data. This basically then can create the videos that we display. For instance, if we want to see the video for 15 radius, you have to run this code for a second. And once the code is complete, we then want to save the hidden state estimations, go to the video blobs, change it to 15, and then this will write the frames I want write. I just want to display it at this point and add the circles. So we will wait for a second, and the same way you see that the white circle is more noisy, whereas the black circle is less noisy. But as the pixel size increase, we see that the effect is reduced. So, and I will briefly show a part where we have 20 pixels of radius. Excuse me. Yes. And this is for 20 pixels. Where now you can see the blob detection and the hidden state estimations are pretty much acting very similarly. Even if there is a difference, the difference are in the levels of a few pixels over these areas when these G3 measurements start to occur, because actually we don't see half of the plane, which is a big problem. But here actually you see that when half of the plane is out of the current view, hidden state estimation performs better because it actually considers dynamics rather than this instantaneous estimation with the blob fitting. So the system consists of the following building blocks. We acquire the video frames. We use adaptive background estimation using the Correntropy filter, which I have introduced in IJCNN 2011. We then do foreground mask extraction. We use the blob detection algorithm by Alexander Farley. We use state estimation using Ramachandra's model by various hidden state estimators. These hidden state estimators include the common filter, the Correntropy filter, and the fixed point Correntropy filter with adaptive kernel size and fixed kernel size, which I have introduced in IJCNN 2012. We then print the detected locations on the video frame and then display the video. So the overall system have not been implemented using these building blocks before. This is a novel contribution because we, for the first time, use the Correntropy filter background estimation, then do mask foreground extraction, blob detection, and then tracking on the same video. This overall framework, overall pipeline is built for the first time. We observed that for smaller radius, for blob detection, the algorithm does not have a bias, doesn't have that fixed shift. On the other hand, it is more noisy. There are faulty detection that creates outliers. Therefore, in this case, the hidden state estimation improves the results by removing the effects of these outliers. Variations of the Correntropy filters are performing better than the Kalman filter, as the Correntropy, as I have said before, intrinsically introduces resistance against outliers. We observed the improvements by looking at the error PDFs, which became narrower and peakier. The algorithm needs further improvement and would perform better with possible research. It was observed that the main bottleneck of the system is the blob detection. Therefore, a different blob detection algorithm can improve the results drastically. For instance, different types of prototype functions can be used with the same algorithm. A very basic idea even is using an iterative approach, using this blob detection algorithm, find the center, then take that patch out of there using our background estimation, and use that patch as a prototype which will better fit the overall shape. So this iterative process can merge the current blob detection with the background estimation that we have and produce better results. These are possible further future research directions. The main advantage of the current system is observed with smaller radius. In the videos that have been created, we see that the output of the hidden state estimator has a more stable estimation. These are the references I have used. I have quite a bit of text from my two papers, which are given in the first and eighth references. I have used the codes that are cited at the fourth and sixth. One of them is the blob detection. I'm sorry, the sixth and the seventh. One of them is the blob detection, and the second one is displaying the circles on the frames, which I have taken and modified. Thank you very much for listening to this talk. I hope it was interesting and informing.